All right, let's dive right into one of the biggest, most fundamental ideas in all of physics. We're going to look at a paper that asks a really fascinating what if. It's a mathematical thought experiment that dares to peek beyond a barrier we've always been told is absolute.
So if you ask any physicist what's the fastest you can possibly go, you're going to get a very clear, very famous answer. It's a number that basically underpins our entire understanding of the cosmos.
Yep, you got it. The speed of light, about 300,000 kilometers per second. And look, this isn't just a guideline or a suggestion. It's supposed to be a fundamental wall, just baked right into the fabric of reality. That's the world according to Albert Einstein.
But what if there's a loophole, a kind of mathematical backdoor? That's the incredible question posed by a 2012 paper from physicists James Hill and Barry Cox. And the cool part is, they didn't try to break Einstein's physics, they used his own toolkit to see just how far it could go.
Okay, so to really get why their idea is so clever, we first need a quick refresher on why this wall is considered so totally, completely unbreakable in the first place.
It all boils down to Einstein's theory of special relativity. I mean, this thing has been tested and proven right for over a century, and it's built on a couple of solid gold principles, including the idea that the speed of light is constant, no matter what.
And here's the kicker that comes out of that theory. There's a huge problem for anything that actually has mass. You know, like you, me, a planet, a spaceship, if it tries to get anywhere near the speed of light.
So according to Einstein, the faster you go, the more energy it takes to speed you up even more. It's not a linear thing. As you get closer and closer to the speed of light, your mass just balloons. It blows up, approaching infinity, which means you'd need an infinite amount of energy to push you any faster. Yeah, game over.
So, an infinite barrier. That sounds pretty final, right? How could anyone possibly get around that? Well, this is where Hill and Cox get really interesting, because they found a way to sidestep the problem without actually breaking Einstein's rules.
You see, their move was just so elegant. Lots of older theories had to invent some pretty wild, exotic stuff, like using imaginary numbers for mass or something, just to make the math work. But Hill and Cox realized, hey, we don't have to. They just took Einstein's existing equations and logically followed them into that unexplored territory beyond the speed of light.
They weren't trying to poke holes in Einstein's masterpiece. Not at all. They were just curious. They were asking, what happens if we just keep following the math, even past the point where it seems to totally break down? Where does it actually lead?
Okay, so what does this all actually mean? Let's get to the consequences. Because this is where their idea builds into a truly bizarre but mathematically sound new picture of the universe. What they found is that if faster-than-light travel is possible, it wouldn't be like just hitting the accelerator and blowing past light speed. No, instead, the universe of motion would be split into two completely separate domains.
Picture it like this. There are two cosmic highways that never, ever cross. There's the S-subhighway. That's us, the subliminal world, where everything moves slower than light. And then there's the S-superhighway, the superluminal world, where everything is already moving faster than light relative to us. You're born on one highway, and you stay on it.
Now here's the really mind-bending part. If you were on a spaceship cruising down that S-sub-highway, other S-sub-ships wouldn't be zipping past you at crazy faster-than-light speeds. From your point of view, they'd all be moving at normal, sublight speeds. The cosmic speed limit is still the law of the land, even on their crazy superhighway.
And because you have these two completely separate worlds, the old rules for how you add up speeds, yeah, you can just throw those right out the window. Things get very, very counterintuitive.
Okay, check this out. The first two rows, yeah, they make perfect sense. Subliminal plus subliminal equals subliminal. Super plus sub equals super. Got it. But look at that last row. This is where it gets absolutely nuts. It says if you're on a superluminal ship and you fire a superluminal probe, someone back on Earth would see that probe moving slower than light. Adding two faster-than-light speeds gets you a slower-than-light one. Wild, right?
And just when you think it can't get any weirder, it does. The theory doesn't just stop with these strange rules. It actually leaves us with one final fascinating puzzle that the math alone can't answer.
Turns out, when Hill and Cox followed the equations into that superluminal S-sup realm, the math didn't give them one clear answer for how that universe would work. It gave them two equally valid possibilities. Okay, so possibility number one is, well, it's weird, but it's kind of familiar. Space and time would still behave locally in a way we'd recognize. But possibility number two, that one's just straight up alien. It suggests that crossing that light barrier fundamentally flips the rules, creating a reality where space and time behave in a completely new way that we can barely imagine.
And the authors themselves put it perfectly. The idea is that reality itself could literally fork at the speed of light, splitting into two equally plausible paths. The math works for both. The only question is, if that superluminal world exists, which path did nature choose?
And that's the incredible thought we're left with. Now look, this is all a mathematical exploration for now. But it's an amazing example of how even our most solid laws of physics might have these hidden complexities. If a universe beyond the speed of light is even mathematically conceivable, it forces us to ask, what kind of universe do we really live in? And what other rules might be out there operating in places we just can't see yet?
You know, what if the ultimate speed limit in the universe isn't really a wall, but a doorway? For 100 years, physics has basically told us that nothing with mass can go faster than light, period. But today, we're going to dive into this really fascinating paper from 2012 that kind of peeks through that doorway and asks, hey, what would the physics on the other side even look like?
So it all starts with this one big question, right? It's something that's captivated scientists and, let's be honest, all of us science fiction fans for a century. Is the speed of light, that famous letter C, truly the final frontier for how fast things can go? Or is that cosmic speed limit maybe hiding something from us?
For a long, long time, the answer has been a hard yes, it's the limit. And it all boils down to this one incredible equation from Einstein's special relativity. Just look at the bottom part of that fraction. As your velocity, v, gets closer and closer to c, the speed of light, that whole term on the bottom gets smaller and smaller, and it gets really, really close to zero.
And what happens when that denominator actually hits zero? Well, you're trying to divide by zero. The math it shatters. The mass of whatever object you're talking about shoots off to infinity. And this isn't just a theory, it's a mathematical singularity, a hard wall. For decades, that was pretty much the end of the story. But then, back in 2012, two physicists, James Hill and Barry Cox, they came along and decided to look at this so-called wall from a totally different angle. Their paper basically asked, what if this singularity isn't an endpoint? What if it's actually a transition, a doorway to a whole new set of physical rules?
So, how in the world did they do that? Well, they didn't just throw out Einstein's work, not at all. Instead, they took his mathematical engine, but they decided to start it from a completely different place. See, Einstein's theory is built from the perspective of an object that's at rest, where velocity is zero. Hill and Cox asked, okay, but what happens if we start from the other extreme? What if we start from a velocity of infinity?
And this, right here, is where their thinking completely flips our reality on its head. In our universe, the one we know and love, things start out at rest. They have some mass, right? But they have zero momentum. But in this hypothetical faster-than-light universe, objects would start at infinite speed, have zero mass, but they'd have a finite amount of momentum. It is a perfect, bizarre mirror image of our world.
But here's the real kicker. Here's the part that nobody saw coming when they started from infinity. The math didn't just spit out one new theory, it gave them two. It's like the math itself branched off, creating two totally separate, self-consistent, and equally valid sets of rules for a universe beyond the light barrier.
So what are these two possible realities? Well, the paper outlines these two mathematical transformations. The first one is, a more intuitive continuation of the physics we already know, but the second one is fascinating. It goes in and directly tinkers with the exact part of the equation that breaks down at light speed. The wild part is, both of them are mathematically solid. They just paint slightly different pictures of what a superluminal universe would look like.
So this leads to this truly bizarre picture of the cosmos, where reality is sort of split in two. You've got S sub, which is our world, everything moving slower than light. And then you have S sup, the superluminal world. And the way these two realms would see each other, that's where things get really, really strange.
And the key to understanding this bizarre relationship is the velocity addition formula. The rule for how you combine speeds. Hill and Cox found that the same basic formula can apply to both the S sub and S sup worlds. But the results it gives you are, well, let's just say they are not what you would expect at all. Okay, so check this out. In our world, you add two sublight speeds together, you get another sublight speed. Simple enough? You add a sublight speed to a faster-than-light speed, you still get a faster-than-light speed. Okay, that tracks. But Here's the part that just breaks your brain. If you, from our slow-light universe, were to watch two objects in the fast-light universe combine their speeds, their total speed relative to you could actually wind up being slower than light. Yeah, two super-fast speeds can add up to a slow one.
And this whole mirror image logic, it doesn't stop with speed. It extends to energy too. For us, to get an object to the speed of light would take an infinite amount of energy. But in this FTL world, the complete opposite is true. It would take an infinite amount of energy just to slow down to the speed of light. It's as if the light barrier is this energy wall that you can't cross from either side, locking each reality into its own little domain.
So this brings us all the way back to the central question, doesn't it? If this faster-than-light realm is mathematically possible, and there are two potential rulebooks for how it works, which one would reality actually follow? Which one is the real one?
And the honest answer from the paper is, we have no idea. The authors make it really clear that their goal wasn't to prove that faster-than-light travel exists, it was just show that you can build a mathematically sound theory for it without having to resort to imaginary numbers or other weird tricks. They simply mapped out two possible roads you could take once you go beyond the light barrier.
And that leaves us with this final, really provocative idea, and this is straight from their conclusion. The possibility that reality itself isn't just one set of rules, but that it could actually bifurcate, split in two at the speed of light, branching into two different but equally plausible physical universes. I mean, just think about that for a second, that our entire cosmos might just be one of two possible realities, separated only by a barrier made of light.